Greetings to everyone. This is Rani, PL in Physics from TTWRDC in Nagarkurnool. So, as part of first online lecture, so today I'm going to deal the topic from the paper Electromagnetism, and the topic is Gauss law and its applications. So I would like to discuss today Gauss law and its applications. So the contents for today are, I would also deal about electromagnetic theory introduction. I'll give a brief introduction about electromagnetic theory, and then we'll discuss on a brief, we'll just brush on about the vector analysis, because as it's very important to deal electromagnetic theory. So let's just brush on some of the basics of vector analysis, and then I'll go for the Gauss law. That's a very basic law which deals with the electrostatics, Gauss law, and then Gaussian surfaces. And lastly, I'll end up with the applications of Gauss law. So regarding the history of electromagnetic theory, so this is a theory of electromagnetism, which is also known as classical electromagnetism, was developed by physicists like Coulomb, Ampere, Faraday, and Maxwell. I mean, we have many laws on their names also. We have Coulomb's law, Ampere's law, Faraday's law. So it's in regard of respect to them. So we have a lot of laws on the names, and it's also very important scientist. That is, we have Hans Christian Ørsted, who first discovered the relation between electric and magnetic fields, which resulted in electromagnetic theory. So this person, Ørsted, he's discovered a very important experiment relating electricity and magnetism. He has conducted an experiment. So he discovered the relation between electricity and magnetism. So where a strong electricity creates a magnetic field, and it is such strong that it could turn a magnetic compass. Could turn the needle of the compass. So using the electricity. So the basic idea of electromagnetism or electromagnetic theory has started from this person Ørsted by that experiment, by that very great experiment. I would say that breakthrough experiment, Ørsted experiment. So let me go to the next slide. So I discussed the overview of electromagnetic theory. Electromagnetic theory has four parts: electrostatics, magnetostatics, electromagnetic waves, and geometric optics. So electrostatics, we all know that electrostatics is a branch of electromagnetic theory where it deals with the charges in rest position. So when you have the charges, that is the electric charges, the study of those electric charges comes under the electrostatics. And magnetostatics is also a branch of this one, so which deals with the charges in motion, or charges which gets accelerated and as they are in the motion. So the study of those charges that comes under the magnetostatics. So magnetostatics is like magnetic analog to the electrostatics. So it also deals about the steady currents. And all such topics comes under the magnetostatics. And we know that electromagnetic wave, as the name itself has electro and magnet. So it's a combination of both electrostatics and magnetostatics. So where there is electromagnetic wave, so it's nothing but the electric and magnetic fields when they vary with respect to the time. When they vary with respect to the time, so there are some electromagnetic waves, and we have a lot of theory that goes into this electromagnetic theory, electromagnetic waves. And this transmission theory, it's a new one. I also just heard when I was Googling, when I had Googled about all the basics and overview of this electromagnetic theory. So this transmission theory, so it explains about the results in terms of forward and reflected wave. We have whenever you have EM wave, when you have taken across a boundary. So you have a transmission, reflector, and refractor wave. So it's just the study about those things in terms of forward and reflected wave. And the two components, so the reflector and forward, they combine, they sum each other, and summing it each end to satisfy the boundary condition. At what boundary? So this forward and reflected wave. So it all deals about that one, transmission line theory, and another one is geometric optics. As we all know that geometric optics or ray optics is a model of optics, so that it creates light propagation in terms of rays. So this is the overview of electromagnetic theory. So let me also tell you about electromagnetic field theory. So when you know, let's just briefly discuss about this one. So when an event takes place and has an effect on something at a different location, we talk about that event as being connected by a field, right? So whenever something happens at some place and it has an effect on some different location, so this is connected by a field, right? So that field is nothing but a spatial distribution of quantity, nothing but this space. So in general, it can either be a scalar or a vector. So this spatial distribution in general can be a scalar or a vector. Nothing but the physical quantity. So it can be a scalar or a vector. So this electromagnetic field theory is the study of forces between charged particles which vary in magnitude and direction. As we know that this scalars and vector, scalar is a magnetism, is a physical quantity which has magnitude, and vector which has both magnitude and direction. So which vary in magnitude and direction with time and throughout space. So that the theory is a heavy user of vector differential and integral calculus. So this electromagnetic field is a study of and charged particles. So as they vary in magnitude and direction with respect to time and in the space. So this theory is a heavy user of vectors because we are talking this physical quantities or the forces or the charged particles in terms of the vectors and scalars. So this electromagnetic field theory or the electromagnetism is a heavy user of vector differentiation and integral calculus. So the main thing what I would like to tell you here is this electromagnetic theory is complete application of vector analysis and vector calculus. So we discuss the laws, principles of this electromagnetics in terms of the vector formulas and the vector analysis and calculus. So that is the one thing. So physical formula gives the applications of physics. So vector analysis provides an efficient way for representing physical laws. So particularly in electromagnetism, vector analysis brings to the forefront the physical ideas, thoughts involved in the equations. So that's why this vector analysis is a very important one to deal the electromagnetism topic. We'll go to the next one. So I'll just give a quick review on vector analysis. So as we all know, this vector analysis is very basic one. So vectors, the product vector vectors, dot product and Gauss product. So the dot product, two vectors A and B, so now having an angle theta. So the dot product A dot B is mod A mod B cos theta. Okay. And here the A is perpendicular to B. The dot product will be C. And the cross product, the same A and B vectors having the theta between them. So the dot product given, cross product given as C plus B is equal to mod A mod B sin theta. And here if A is parallel to B, the cross product of A and B is 0. So parallel in the sense you have theta is 0 and sin 0 will be 0 here in the cross product. And here theta will be 90 in the perpendicular cos. I'm sorry. Yeah, A is perpendicular to B, so theta is 90. So then the dot product here is 0. Here if it is parallel, then it is 0. Yeah. The next topic I'd like to discuss is vector derivatives. So this is very, very important to deal with the electromagnetic. So we know the vector derivatives. We have the vector derivatives. We have divergence, curl, and gradient. Right? So first of all, del. We all know that the del is an operator. So which acts on some vectors. Del operator is dou by dou x I cap or x cap plus dou by dou y j cap k cap y cap plus dou by dou z k cap or z. So that's the del operator. And the first one is the gradient. So gradient of a gradient of a scalar function. So we operate the gradient on a scalar function. Points in the direction of maximum increase of function. So this gradient is going to point in a direction of maximum increase of function. It tells about how far the function varies if we move a little bit. So how does the function vary? So that is going to be told by this gradient. So the gradient points in the direction of steepest level, as in it points or it gives the direction of maximum increase of the function. So the gradient we operate it on a scalar. So let f is a scalar. Del f equals the operator del operator dou by dou x I cap I cap plus j cap plus k cap. So dou f by dou x into I cap plus dou f by dou y into j cap. So here we have only taken the components, leaving the I cap, j cap, and k cap. So this is very easy. The divergence and curl of vector field. So the divergence of a vector and the curl of a vector. So divergence, as by the name itself, it says divergence. So divergence means it moves into space, so like this, it diverges. So divergence is also nothing but the operating this del operator on a vector, right? So del dot in the dot product format, right? So del dot f or del dot a or del dot any vector that gives that divergence. So divergence measures how much the vector b spreads out from a point. So the divergence, how much this vector is spreading into the space. So how much it is spreading from a given point. So that is given by the divergence. So for example, to understand this divergence, so imagine you are at a pond or something, some water, and you are dropping some let's say you are dropping some sawdust, the very fine powder you are just dropping it into the pond. And if you imagine if those are coming or if they are diverging. So if they are diverging, so that means you have a positive divergence. And if they are coming together to a point, so everything is coming to the same point. So that means you have a negative divergence. So divergence is like this. So positive divergence and negative divergence. So for the positive divergence, it's known as the source or faucet. And for the negative divergence, that is known as the sink or it's called a drain. The divergence is non-zero if there are sources or sinks. So that's what it is given here. So if you see the arrows, so from a given point, it is divergent. More the bigger the arrows, that means the divergence is more if the point very near to that. And as it's going, so you see a smaller arrows, so that divergence is kind of decreasing. So it tells about a vector, how much it is divergent. And similarly, the curl of the vector function. So curl of the vector is the same operating the del on a vector in the cross product form. Del cross. Right? So del cross is the curl of the vector. And this one, the physical interpretation of this curl is it measures how much the vector curls around. So curling isn't nothing but the rotating. So how much it rotates or curls. So that is given by this one. And to understand this also, you can imagine standing at some pond or somewhere you have some kind of water, and if you drop a cork or rubber cork with pigs, so if you just drop it and if it rotates as soon as it drops, so you can say that your case is a non-zero. The curl in the sense rotation. Having rotation is nothing but the. So you can see here also. So you have an X and Y plane, so where you can see the rotation. So that means the curling of that vector. So So the functions that tend to curl around have large parts. So whichever the functions they curl, nothing that they rotate, they have the large curls. So this is about that. And yeah, Gauss divergence and Stokes theorem. So we know the very basic theorems in the vector analysis. So Gauss divergence theorem states that relates that the flux of a vector field when it goes to surface to the divergence of the field in the volume integral. So it is basically converting the surface to a volume integral. So mathematically, surface integral A dot ds equal to volume integral del dot A into D. So the flux of the vector field, when you close the surface, the flux of the vector field is equal to the divergence of the field in the volume enclosed. In the same volume enclosed, divergence, it is equal to the divergence of the field. Flux of the vector field is equal to the divergence of the field. So that is Gauss divergence theorem. And Stokes theorem states that the surface integral of the curl of a function over any surface bounded by a closed path is equals to the line integral of a particular vector function around that path. So a very easy note, you can also say that the Stokes theorem is the conversion of line integral to the surface integral. Surface integral of the curl of a function. So if you imagine any function, the surface integral of the curl of the function or any closed bounded or closed path is equal to line integral of the particular function around that path. So there's a function and the curl of that function around a closed path is equals to line integral of the particular vector function around that path. So conversion of line to surface, Stokes theorem. So line integral of line integral or nothing but a closed curve. Closed curve over C dot dl is equal to surface integral del cross A into ds. This is Stokes theorem. Now we'll go to the Gauss law. So Gauss law was given by the German physicist and mathematician called Friedrich Gauss. So upon his name, this law is named as Gauss law. So Gauss law is, as we all know, Gauss law relates about the flux when it closed the surface is a measure of charge closed with the surface. Any charge outside the surface doesn't contribute any flux. Right? So we know that the Gauss law basically relates about how the flux and the charge is entered, how it is related. Right? So the flux, the electric flux phi e, and how it is related with the charge Q. We know the mathematical Gauss-law equation is phi is equal to Q by epsilon. But what is phi? What is electric flux? Electric flux is nothing but the number of electric lines of force passing through a given area. Right? So that is mathematically electric flux is phi is equal to integration E dot ds. Right? Integration E dot ds or integration E dot d. Now, this electric flux is equals to the flux phi Q by epsilon. So that one, Gauss law is relating about the charge and the electric flux. So the relation between these two is given by the Gauss law. So the electric flux out of the closed surface is equal to charge and Q divided by the permittivity. So that's why phi the electric flux is equal to Q by epsilon. Right? So when the charge is at the center of the sphere, the electric field, we'll see how if the charge is at the center of the sphere, and how the electric field and what is going to be the Gauss law. We'll take a very simple case when the charge is at the center of the sphere. So the electric field is everywhere normal to the surface and constant in magnitude. So this is the charge, and this charge is at the center of the So this is the charge, and this is at the center of the sphere. So, and this electric field is everywhere normal to the surface and constant in magnitude. So to find Gauss law, we need to assume a Gaussian surface around this one. So we need to observe a surface or a Gaussian surface around this one. Why Gaussian surface and what is Gaussian surface, I'll explain in a bit later in the next slide. So I can just quickly tell you that I'm saying that the Gauss law phi is equal to first integration the ds equal to q by epsilon, right? So the flux is relating with the electric, and the electric field is not only electric field. Integration with the field, so it is relating to the surface around where the charge is present. So to know that, we have to assume a Gaussian surface, which is an imaginary surface. So we are assuming Gaussian, spherical Gaussian surface here, radius r. So we are just taking a spherical Gaussian surface with the charge to be present in the center. So a positive point charge field is surrounded by an imaginary sphere of radius. So that imaginary sphere is we just assuming to find what is the flux through this charge. Right? So this is a charge Q, and that is this Gaussian surface of radius r, Gaussian sphere of radius r. So the total electric flux through the closed surface of the sphere. So now the total electric flux, whatever the electric flux, the electric lines of force are moving through this one, is nothing but the electric flux. That one we can derive it from the equation phi is equal to force integration e dot d or e dot dx. Right? So this dA is nothing but this within the Gaussian surface, within that area. So let us just assume this dA is the small amount of area, that is the area. And that A is the small amount of area. dA bar is the non-surface normal. So surface normal is nothing but whenever you are taking a surface, so the surface normal is nothing but the vector which is perpendicular to that surface, right? So that's why we are taking a small area here. So dA bar points in this direction. So integration E bar dot dA bar. So that is the dot product can be written as integration dA cos theta. Right? So the dot product of two vectors is dA cos theta. So the now electric field of the point charge is directed radially outward at all points in the surface of the sphere. So whenever there is a charge, and the charge always spreads out radially outward within the space around it. Right? So the electric field of the point charge is directed radially outward. So therefore the direction of the area element dA is along the electric field. Right? So let's say E is in this direction. So E is also in this direction. So E is in this direction and dA is in this direction. So both are in the same direction. So theta is 0. So once theta is 0, phi is equal to integration E dA cos 0. Cos 0 is 1. So integration E into d. Right? So I'll just go to the next slide. So phi is equal to integration ED because cos 0 is 1. So now E is uniform on the surface of the sphere. Right? So E is uniform on the surface of the sphere. It's constant. And the value is constant. It's uniform. So phi is equal to E. E can be taken out since it's not varying. So E integration D. So now in substituting for integration dA is nothing but you have taken dA is the small amount of area. So now this dA is nothing but the total area of the sphere. So the dA, all the parts adding up as you are integrating. So dA becomes the total area of the sphere. So we know that the area of the sphere is 4 pi r square. Right? And just substituting it, and E is equal to 1 by 4 pi epsilon 1 cubic. So this equation is directly. So let me go to the last slide and explain you how E is equal to 1 by 4 pi epsilon Q by R square. Right. So at this point, we have taken the direction as the direction. The direction is radially outward into the space, which is parallel to the dA bar, the normal area vector, the normal surface vector. So what about the value of E? Since E is a vector, it has the magnitude and direction. So direction is clear. It's along dA. Now what about the value of E, magnitude? Right? So to find magnitude, so let us place a test charge, a unit test charge at this point, +1. So whenever you have to find the electric field at some point, you have to place a unit test charge. Unit test charge since the charge whose value is 1. Right? So you just have to place a unit test charge here. So place a unit test charge here. So that is +1. Right? So here it is +1 and here it is +2. Right. And you know E is equal to the formula F by Q. You know this formula is equal to in the very basics of electrostatics, you know, is called F by Q, where F is Coulomb's force between the two charges. So here is a discharge +1 and here is the actual charge Q. So what is Coulomb's law? Coulomb's law is F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R. So let's say Q1 is Q and Q2 is +1, right? So what happens to the F? So that is E is equal to 1 by 4 pi So 1 by 4 pi epsilon naught Q1 Q2. So you just have the two charges. One is the +Q and one is another test charge. So Q into 1, capital Q, which is in the numerator, capital Q into 1 pi. And the distance between this charge and this one, this is nothing but R. R is sphere and R is the radius of the sphere. It doesn't change. So this is R square. So we got F, right? So by Q, the Q which you are taking this one, the test charge. So that will be the +1. So finally, E is equal to Q by 4 pi epsilon naught into R square. So that is the magnitude. Now, so T is equal to 1 by 4 pi epsilon naught Q by R square. Now substituting this value in the other equation, 1 by 4 pi epsilon naught capital Q by R square into 4 pi R square. 4 pi gets cancelled. So that is Q is equal to and R square R square. 4 pi and R square get cancelled. So pi is equal to Q by R square. So this equation is known as Gauss. So pi is the electric flux. Pi is equal to integration TTWRDC equal to Q by epsilon. So it's a relation between the charge and the flux. You have a charge and how much the charge, I mean, what is the amount of flux passing through the surface due to the charge, right? So that relation is given by the Gauss law. This is Gauss law. Now we'll discuss the Gaussian surfaces. So the net flux is the same throughout all the surfaces. So you need to consider a Gaussian surface in order to find the electric field. So the main essence of this Gauss law is nothing but to find the electric field. So using Gauss law, one can find the electric field because in phi, the electric flux phi is equal to integration E dot ds is equal to Q by epsilon. So there's E associated with the surface integral, right? So using that relation, we find the electric field. And those are the applications of Gauss law. So now let me just explain Gaussian surfaces. So as Gauss law does not provide expression for E. So as Gauss law does not provide expression for E, but provides only for the surface integral. Right? So So using Gauss law, one cannot write expression for E. What it only provides is it provides expression for E. It doesn't provide expression for E, but provides only for its surface integral, right? Because we have phi is equal to integration E dot ds when this electric field is associated with the surface, right? Integration ds or integration d. So that surface it provides only for this surface integral. So I mean directly you cannot say that using Gauss law one can find electric field and show in application, but not directly. When you associate this E with the surface integral, then you can extract the electric field. Right? We'll see. So to calculate E, we must use a surface in which a way that the surface integral may be replaced by a product of which E is a factor. Right? So to calculate this E, to calculate the electric field, we must use a surface. We have to consider an imaginary surface in such a way that the surface integral may be replaced by a product of which E is a factor. Right? So the surface integral of that surface which you are considering into the E. So that through that way you can calculate E. So mathematical expression itself tells phi is equal to integration E dot ds. Right? So E into the surface integral. So that gives you by solving that gives you the electric field. So this hypothetical surface, in order to find the electric field, whatever the surface you are taking imaginarily, it's an imaginary surface, of course, right? Just to satisfy the equation, phi is equal to integration E dot ds, right? So in order to find the electric field, you are considering an imaginary surface, a hypothetical surface that is known as the Gauss Gaussian surface. So thus the necessary condition for applying Gauss law for calculating E is a uniform and symmetrical charge distribution where the Gaussian surface may also be seen. So generally to calculate electric field, so the charge distribution must also be uniform and symmetrical. Uniform, the charge should be uniform, it should not be varying, and symmetrical. Symmetrical in the sense the charge distribution, it should be symmetrical. Symmetrical means it's the same. If you look at something, if you look the charge, whichever you're going to consider it to some point, it should look symmetrical, not the same. Symmetrical in the sense the same this. If you look at from the both sides, it should be the same. So symmetry is crucial to the application of Gauss, right? And when symmetry permits, so it affords by far the quickest and easiest way of computing electric fields. So whenever there is symmetry in the charge distribution, so it's very easy to calculate electric field. So that's why we say that symmetry is very crucial to the application of Gauss. So it makes our life easy when there is symmetry within the charge distribution. Let us see the types of Gaussian surfaces. So there are three types. As far as I know, there are three types. So spherical symmetry. Yeah, spherical symmetry, as in the charge, when there is the charge is spherically symmetry. So then you have to consider or make your Gaussian surface a constant scheme. Right? So for a spherical symmetry, whenever you have a charge and the charge is spherically symmetric, so here to find the electric field, you have to consider a Gaussian surface which is concentric. And for the cylindrical symmetry charge distribution, there you should consider a Gaussian surface of coaxial cylinder shape, the Gaussian surface symmetry. For plane symmetry, use a Gaussian pillbox, so which straddles the surface. So pillbox in the sense you have this one, like you have the two holes and connected by a fiber speaking, so that's called a pillbox. So that's a Gaussian pillbox. You need to consider for the plane symmetry. So these are the types of Gaussian surfaces, and the conditions for the Gaussian surface over which the Gauss law is applied must be placed. So wherever you are considering the surface to find the electric field using Gauss law, so So that imaginary surface has to be used. And at each point of the surface, the is the displacement vector, which is nothing but D is epsilon naught T. The permittivity into the electric field is either normal or tangential. So that is perpendicular to band. So at each point of this Gaussian surface, the C or D, it should either be normal or tangential. So these are some of the conditions which I know, and types are this. So that's about the Gaussian surfaces. Now we'll go for the applications. I'll discuss the first application. Today I'm going to discuss the three applications. It's like 1D, 2D, and 3D. So the first application I'm going to discuss is electric field due to an infinitely long charged wire. So due to a long charged wire, so you need to find an electric field due to that. So consider an infinitely long straight wire having the uniform linear charge density lambda. Right? So we need to consider a long pictures are in the next slide. Let me just speed out. So you consider a long straight wire having uniform linear charge density lambda. The charge, there are three types of charge densities: linear charge density, surface charge density, and volume charge density. Linear charge density is represented with lambda. That is charge per length. Q by L is linear charge density, and the surface charge density is charge per area. Q by A is surface charge density sigma, and volume charge density represented with rho. Rho is equal to Q by A. Charge per volume is volume charge density. So due to this long straight wire, you need to calculate electric field. It's all about yeah. So within the figure A, you have a long straight wire where the charges are present within the wire. So due to this one, at a distance of r, at point B, we need to calculate electric field. So what is the amount of electric field existing at point B due to this wire? Right, that one we have to find out. So this we are going to find out using the Gauss law. So now to find this one, we need to consider a ring to assume certain things here. So as I told you here, so electric field. So yeah, of course these are the applications of Gauss law. So of course we are going to find electric field using this Gauss law. So we chose two small charge elements A1 and A2 on the wire, which are at equal distances from the point. The result of the electric field due to these two charge elements points radially away, so that the charge wire and the magnitude of the electric field is same at all the points in the circle of radius. Yes, so to find that, so the electric field at point P due to this infinitely long charged wire we need to find. So to find at this point, so at P point, if you just stand at the P point and look it on either sides of this wire, it looks the same. So there is no change within the configuration of the wire. So this is one kind of symmetry. So this is called the symmetric charge distribution. It's not asymmetric. Asymmetric where you see different type of configurations on either side, but it's same. Right? So here you're considering A1 and A2, the two A1 and A2 charge elements which are at equal distance from the point. Now the resultant electric field due to these two charge elements points radially away from the charged wire. The magnitude of electric field is same within the circle. So the charges due to these two charge elements A1 and A2 on either sides of the points in P and Q, they point radially away. The value will be equal, but they point radially away. So the value of electric field will be same on this circle. Anywhere on the circle, the value will be the same. So to find the electric field at this P point, we need to consider a Gaussian surface. So let us choose a cylindrical Gaussian surface of radius smaller and length. We are choosing the cylindrical Gaussian surface of radius smaller and length of the Gaussian surface is cylindrical Gaussian surface is L. Now the total electric flux in this closed surface is calculated as follows. So let us see how this electric flux is going to be calculated. So we have three parts. You know the electric flux phi is equal to integration E dot d. Right? So now this one we're going to divide it into three parts. That is, you have one top surface, one bottom surface, and one the middle surface. Just imagine a cylinder of like this. You have a top surface, you have the middle curved surface, and you have the bottom surface. So there are three parts within this cylindrical Gaussian surface. So that's why we're just dividing this integral into the three parts. So integral curved surface we dot dA, and okay, so we are just dividing this one into the three parts. So curved surface we dot dA plus top surface plus bottom surface. So now you see clearly the top surface and the bottom surface. So it's like so on the top surface, this is the top surface, the bottom surface. So now this is a book, but that's why you see a hole here. But for a cylinder, everything is a closed one here. So this is the surface. So the surface normally would point upward. Whenever you take the surface normal, it should be perpendicular to the surface which you are considering. So the surface normal points upwards, and for the down point, it points down. So you see this end cap, that is the surface normal. So it is pointing downward for the top bottom part and upward for the top part. And now this electric field, it is radially outward. So you have the charges and acting radially outward. So at the top and bottom surface, E is perpendicular to this end cap, right? It's making an angle 90. So that is this ds bar. This end cap is nothing but the dA bar, right? So it's written differently. So it's this E bar and dA bar where they are making an angle 90 to the top and bottom. So once it is making 90, so you can assume they're going to be the flux, they're going to be zero, because E dot dA, if you write it in the full form, that is E dA cos theta. Cos theta is zero. Right? So the total flux going to be zero. The flux is going to be contributed only from the curved part. So in the curved part, if you see E bar and E bar and N bar, the BA bar and D bar both are parallel. The beta is zero. Right? So that is the up and down of the bottom part. Right? So the bottom part contributes flux as E is parallel to ds. So like the bottom part where you have a small amount of ds, which is from the inside. So there the ds bar is parallel to the E. So they both are parallel and it makes an angle theta. So that is the only part which contributes the flux. So E is parallel to ds bar and dA bar, and E dot dA is equal to PT. Right? Cos 0 is 1. So for the top and bottom surfaces, E is perpendicular to dA. So hence E dot dA is 0. So phi is equal to, that is only contributing to the curved surface. So integration curved surface E dot dA is equal to Q enclosed by epsilon from the Gauss law. So from the Gauss law, so integration E dot dA is equal to Q enclosed by epsilon. So since the magnitude of the electric field for the entire curved surface is constant, E is taken out of the integration. E is constant, you know that for the entire curved surface. So we can write it outside the integral. E integral dA is equal to, now Q. I write Q in terms of the charge density, linear charge density. I've just told you that the charge density lambda is Q by M, charge per length. So from there, Q enclosed is equal to lambda into L. So just substituting it here. So that is Q enclosed is lambda into L by epsilon naught. So now integration dA. Integration dA is nothing but the total area of the curved surface. So total area of the substitute this 2 pi RL here. So E into 2 pi RL is equal to lambda L by epsilon. So that is L and L gets cancelled. So E is equal to lambda by 2 epsilon naught, 2 R epsilon naught. So 2 pi by R epsilon naught. So that is the electric field due to an infinitely long charged wire. So finally we have found out what is electric field at point P due to that infinitely charged wire. P is equal to lambda by 2 pi R epsilon. So that is due to that. So we have done the first application. Let's go to the next one. So now here we are considering the plane which we are doing. We'll just consider the plane sheet of charge, and due to this plane sheet of charge, it is going to calculate what is electric field. Right? So consider an infinite plane sheet of charge with uniform surface charge density sigma. Right? So since it's a plane, here exists the surface charge density sigma. You know, sigma is equal to Q by A. Right? So let P be a point at the distance of R from the sheet. And since the plane is infinitely large, the electric field should be same for all points at the distance from the plane. Right? So we just have to consider another Gaussian surface here. Let's see. Okay? Yeah. So this is the infinite plane sheet of charge. Right? So due to this plane sheet of charge, we need to find what is the electric field due to this plane charge at P point. Right? So to find the electric field, since for a plane charge symmetry, as we discussed in the Gaussian surfaces, we have to consider a pillbox. Right? So this is, we are considering the cylindrical surface, or the, let's say, pillbox. So to consider a Gaussian surface, we are taking a cylindrical surface or a pillbox here. So you have other two sides, P and P dash. Right? So at P and P dash, so it's like this one now. Just imagine like the cylinder now horizontal. So it's like the pillbox like this. So P and P dash. So this is the surface. So now dA bar points in this direction, and here this is this one. Now dA bar points in this direction. So here also I have the three parts. The integral is going to be divided into three parts. And the curved part, integral curved surface E dot dA plus integral P E dot dA plus integral P dash E dot dA is equal to Q enclosed by epsilon. That's from the Gauss. Right? Formula is I is equal to integral E dot dA equal to Q by epsilon. Okay. So now this electric field. Now we get to see it all the different cases. Right? So at this point, E is parallel to D. Right? So the flux exists from P and P dash point. So now if you see from the middle part, right? So the middle part, what happens there? This E is pointing away from this plane, right? So E is pointing away from the plane, and the dA bar. So this is like this. Right? This is P and P dash. The surface part, the inner part. Just imagine the inner part of this one, right? So there, the inner part, there you have to consider a small amount of dA. So dA bar will be perpendicular to P. So like this, right? So now here inside one, here you have to consider the dA. Right? So this is dA. Now dA points away. It points perpendicularly to P. E points in this direction. Now this here we are considering this one, this side here. Okay? So let's say here Nagarkurnool here. So dA is nothing but it points upwards. Since you are taking the middle curve. So there it is perpendicular. So as it is E is perpendicular, no flux coming out from the curved surface, only it comes from the P and P dash. Right? So that is anyway 0. So now I'm directly writing it. Phi is equal to integral P EDA plus integral P dash EDA. Now I have removed the dot product. So why? Because cos 0. Cos 0 is 1. Right? So EDA cos 0. EDA cos 0. Cos 0 is 1. So integral EDA plus integral EDA. So this happens. So just it. Yeah, so this becomes integral EDA, so integral to E also I can write outside the integral, so 2E integral dA, so integral dA is equal to, now Q, I write Q also in terms of sigma, what is Q in terms of sigma? Q sigma into A, because we know sigma is Q by A. Okay, so now, so 2E and integration dA. So integration dA will be A. So is equal to, there is an epsilon naught already now. So this is sigma U. So the A and another A where it's cancelled. So finally E is equal to sigma by 2 epsilon. So that is that's the electric field within the plane sheet of charge. So finally E is equal to sigma by 2 epsilon naught is the amount of electric field due to an infinite plane sheet of charge. So we have drawn out some of the points for allocating them. The electric field due to an infinite plane sheet of charge depends on the surface charge density and is independent of the distance of Earth. So finally what we have got is we have got E as E is equal to sigma by 2 epsilon naught, where electric field due to an infinite plane sheet of charge is dependent only on sigma, that is surface charge density, and epsilon naught, and it is independent of the distance of R. Wherever you take the R value, goes to the plane sheet of charge and away from it, but it depends only on the sigma, surface charge density. And the electric field will be the same at any point further away from the charged plane. So that's what just told you, that's the point. And if sigma is greater than 0, that surface charge density, if it is greater than 0, the electric field at any point P is outward perpendicular to the plane. And if it's less than 0, the electric field points inward perpendicularly to the plane. So that is the second application. And third one, let me just quickly go. I think we're running out of time. So the electric field due to uniformly charged spherical surface. So we just consider a spherical surface. Yeah, so this is a spherical surface. So we have to consider the uniformly charged spherical shell of radius r and total charge q. So we need to consider a sphere of radius r and total charge q. The electric field at points outside and inside the charged sphere is found using Gauss. So we have to find the electric field due to the spherical shell, right? So we have three cases at a point outside, inside, and on. So that one we have to find out. So let us go for the case A. So here, if you see the A for the points outside the sphere, a large spherical Gaussian surface. So that's what the Gaussian surfaces have the charge distribution as a spherical shell. But you have to take the Gaussian surface, you have to take a spherical Gaussian surface. So that's why we are considering the spherical Gaussian surface. So the inside one is the actual sphere of radius capital R and capital Q is the charge. And now the radius of small r, and you are taking a Gaussian surface. So it's an imaginary Gaussian sphere. That surface is only known as Gaussian sphere. So the points outside the sphere, a large spherical Gaussian surface is drawn concentric in the sphere. And now the second case, for the points inside the sphere, a spherical Gaussian surface smaller than the sphere is drawn. So this first one, A is outside and B is inside. Inside is we are taking a Gaussian surface of radius smaller and we are considering the point P. At this point P, you have to find the electric field in both the cases. Right, so let us go. So we choose a spherical Gaussian surface of radius R. Radius R is chosen and the total charge enclosed by the Gaussian surface is Q. So applying Gauss law, integration d dot dA is equal to Q by epsilon. And the electric field E and dA bar point in the same direction, outward normal at all points in the Gaussian surface. So the magnitude of E is also the same at all points due to the spherical symmetry of the charges. Since the charge distribution is spherical symmetry, so the value of E at all points on the imaginary Gaussian sphere is same. E, it points radially outward, and at P point you consider a small so at this P point you consider a small dA, so where it points in the same direction this way, and B will also point in the same direction. Okay. So this one. So integration E, integration E. Anyways, it's same direction. So cos theta is 0. So cos 0 is 1. So E integration E is constant and taking it out of the integral. So E integral dA is equal to Q by epsilon naught. So dA. So dA is nothing but the total area of integral dA is nothing but the total area of the Gaussian surface. So the surface of the sphere we know that is 4 pi r square. But since we have taken the radius of the Gaussian surface as smaller, so that will be 4 pi smaller. So E into 4 pi r square equal to Q by epsilon naught. E into 4 pi r square equal to Q by epsilon naught. So E is equal to 1 by 4 pi epsilon naught Q by r square. So this is the radius. This is electric field due to a spherical shell at a point outside this. So if you see 1 by 4 pi is constant, Q is constant. E is inversely proportional to r square. So as you go square of the distance, E is inversely proportional. So as you go far from the sphere, so E will be less. As you are very near, so E will be inversely proportional. Yeah. If you go far, E will be more, and if you are very near, it will be much in magnitude. So in vector form, this just so now the case at point P, at the point of the surface of the spherical shell. So we have three cases: outside, inside, and on the sphere. Right? So on the sphere, so what happens on the sphere? Small r is equal to capital. So the radius of actual spherical shell is equal to the Gaussian surface radius. So if you see here, this is so if you see here, this is the actual sphere. So now on the sphere, in the sense, you will also assume the same Gaussian surface on the sphere. So that means this smaller, if you imagine this Gaussian surface, it is reduced to this point, at this point. It is reduced to this point. So smaller will be equal to capital. So then if you just simply substitute smaller is equal to capital R in the case 1, where the electric field is at a point outside the sphere. So that becomes E is equal to Q 1 by 4 pi epsilon naught Q by capital X. So E is equal to Q by 1 by 4 pi epsilon naught Q by r square. So this is the value of electric field at a point on the surface of the sphere. So if you see clearly 1 by 4 pi epsilon naught is a constant, Q is constant, and capital R is also constant, which is the actual radius of the sphere. That won't change. So electric field at a point on the surface of the sphere is constant. So now this one third case, the point inside the spherical shell. So consider a point P inside the shell at a distance r from the center that we have seen before the this one with the slides, before slides. So let us consider the point P inside the shell at a distance r from the center and Gaussian sphere of radius small r is constant. So integration E dA is equal to Q by epsilon. So E into 4 pi r square is equal to Q by r square. So using Gauss law, integration with the method dA is equal to Q by epsilon naught E into, and this dA is the small amount of area within the Gaussian surface. So now integration with the integration dA will be 4 pi r square equal to Q by epsilon. So but since this Gaussian surface that does not enclose any charge, so charge Q will be 0. So the total electric field that goes to 0, electric field E is equals to 0 for the case when electric field at a point inside the sphere. So for inside the sphere, since there is no charge enclosed, so there will be no electric field. So E is equals to 0 in the third case, that is at a point inside the spherical shell. So the electric field to the charged spherical shell is 0 at all points inside the shell. So inside the shell at all points the electric field is 0. And now we have drawn a graph depicting all the three cases. So inside, outside, and around the sphere. So inside is nothing but where this now this graph is drawn as the radius and the distance r. R is there. You have taken the radius of the Gaussian surface, imaginary Gaussian surface on its axis, and electric field on y axis. So for till r is till the radius of actual surface capital R, which is inside there will be no electric field, so E is 0 here. And after that, the electric field at a point R on the surface of the sphere, that is case 2, we have got a constant value, that is E equal to 1 by 4 epsilon naught Q by capital R. So that's a constant value. So you see a straight line here. So you see a straight line here, and now the third case when R is the radius of the actual sphere and small r is at a small r is the Gaussian surface radius. So at the points outside the radius of the sphere. So that is nothing but the outside points we have got E equal to 1 by 4 epsilon naught Q by small r square. So that is E is inversely proportional to r square of the distance. So we get a decay curve. So that is it is decreasing curve. So this here it depicts all the three cases. So it decreases. This is E. This one represents E. This is E out. And this is E on. Yeah, this right line is E on, and this one is E in. So these are the three applications. So these are the three applications of Gauss law. So one dimension, two dimension, low dimension, wire, and like sheet of charge in this plane. So Gauss law application. So that's it. I have finished all the topics. I hope I'm clear. And thank you all those who are just viewing this.